Good evening, everyone. Welcome to our next in our video set on quadratics. This will be lessons 3 and 4 to go along with our unit 1.5. Here we're going to examine a little bit more one of the things we looked at in our first lesson on what's called the zero product property. So if you remember in our first lesson how we found x-intercepts by looking at factors, we're going to expand on that a little bit more with these two lessons. So let's just get right into it. And button. There. Okay, let's start with a little warm-up. We want to solve some equations, so let's go back and put our Algebra 1 hats on and solve some equations, shall we? Notice how each of these equations have something in common. They all equal 0. And that will be very important for these lessons, as the equations that we're going to work with are all best worked with when there's a 0 on one side of the equation. So let's go ahead and solve a few of these. So the first one, pretty straightforward, right? 6 plus 2a equals 0. Let's subtract 6 from both sides. 2a equals negative 6. Divide by 2. Divide by 2. And a equals negative 3. Okay. And sure enough, negative 3, when plugged in for a, will make this equal to 0. How about over here? 7 times b equals 0. Well, you could just think to yourself logically that 7 times what number gives you 0, or you are allowed to divide both sides by 7. The fact that there is a 0 there does not matter. 0 out of 7 is, well, 0. And so b equals 0, which makes sense, right? 7 times 0 is 0. So remember, what you don't want is to have a 0 in the denominator. That would be a problem. But a 0 in the numerator, no issue. How about this one? 7 times c minus 5 equals 0. Okay, so there's a few ways you can do this, right? You can distribute the 7 like this. You might do 7c minus 35 equals 0. You could do that, and then you would add the 35 to both sides, right? You get 7c equals 35, divide by 7, and c equals 5. So you could do that, but there is another way to do this that's a little bit more straightforward. So I'm going to get rid of that. And let's solve this one a different way than using distribution, because sometimes the distribution might get us into a little trouble. So here, instead of multiplying by 7, I'm going to divide by 7. Now, why am I allowed to do that? Well, because this is 7 multiplied by a factor, and what's the opposite of multiply? Divide. So I can divide both sides by 7, and I get c minus 5 equals, now before 0 divided by 7, that's still 0. So the 7 just, well, vanished. Now the parentheses we don't even need anymore, so we can just write this as c minus 5 equals 0, add the 5 to both sides, c equals 5. Just like that. And here we don't have to mess around with like multiplying to create the 35 or anything like that. And in many ways, this is actually one less step. So this is going to be a common theme throughout this unit. Let's look at the last problem. G times h equals 0. Well, you might remember from Algebra 1 that you can't solve an equation that has two variables in it, right? Well, we could rewrite it though. So g times h equals 0. Well, how do I solve for a variable? Well, let's try something. Let's divide both sides by h, because I have g times h, right? If I try to get rid of one variable, well, I could divide by h. So let's do that. let's divide both sides by h. Well, if we do that, here's what's going to happen. H's go away. Well, what's left on this side? We get 0. And so we get g equals 0. So g equals 0, right? Well, maybe. That's one possibility. Or, what if instead of dividing by h, we divided by g instead? So if I write the original equation, g times h equals 0, but instead I divided by g instead, I would get, the g's would go away, and I'd get h equals 0. So the question is, which is it? Does g equal 0 or does h equal 0? It doesn't matter. And we have to be aware that either one could be possible. So my final answer to this one is g equals 0 or h equals 0. Now, you might remember this from our work last lesson, where I said that if two numbers multiply to give you 0, then one of them has to be a 0. The only way to multiply two numbers together and get 0 is for one of them, or both, to be 0. So this is what's called the zero product property. All right. So essentially, the way that the zero product property works is that anytime I have some quantity in a factor that equals 0, if I have a product of terms, then one of those products should equal 0 if the product itself is also 0. So let's go through a few of those where you see exactly what's happening. Okay, so first one. So again, some more practice here, right? X minus 3 equals 0. Okay, easy enough, right? Add 3 to both sides, right? And so we're going to write it all out. It's a video, so we might as well write it all out. We have time, right? It's not like I'm waiting for like the class bell to ring or anything. X equals 3. And sure enough, 3 minus 3 is 0, right? Same thing here. Subtract 11. X equals negative 11. Same thing here, right? Now there's a 2 in front. So remember, we dealt with this in class by thinking opposite operations, right? We subtract 11 from both sides. I get 2x equals negative 11. Divide by 2. And I get x equals negative 11 over 2. Now, can I turn that to a decimal if I want? It's negative 5.5. I can, but turns out fractions aren't all that bad this unit. And so having a fraction has some benefit. Okay, what about some of these other factors? So you're going to notice going on for the rest of these, you're going to see a lot of the same numbers. But let's take a look at how it works. So number 4, x times 2x plus 11 equals 0. Now, this is the same equation as 3, right? You have this 2x plus 11 equals 0. But you have this x in front of it. And this x multiplied by this factor in parentheses equals 0. But wait a minute. We have a case of one term multiplied by another term. So in order for this to equal 0, one of these two has to equal 0. Generally speaking, only one of them will equal 0. It's pretty rare that you see both of them equal 0 at the same time. So we assume that one of these should be a 0. Like, what happens if I plug in the number 0 itself? Well, if I plug 0 in, I get a 0 here. This factor won't equal 0, right? I'm going to get 11. But I'll get a 0 here. And what's 0 times 11? 0. So it turns out x equals 0 is one answer to this problem. But when I look at this factor over here, this is the same 2x plus 11 that I had before. And its answer will be the same. X equals negative 11 halves. And if you remember, we did this a little bit last unit too, where we took the opposite of the 11 and the opposite of the factor of 2, which is divide by 2. So we have two potential answers here. X equals 0 or x equals negative 11 halves. Either one is correct. But the word or is kind of important because we're being told here that x can't be both numbers at the same time. Only one of them. And if either one of these gets plugged in for x, then this whole product will equal 0. This also means that these are the x-intercepts of this particular graph. And that's what a lot of all this is also doing. When we're finding the solution or solutions, we're also finding x-intercepts. All right, let's continue. What about this one? Now we have two separate factors. We have x minus 3 and x plus 11. Either one of these can equal 0. And so from this factor, x could be 3, right? So because we have if x minus 3 equals 0 or x plus 11 equals 0, then on this side, 3 works. And on this side, negative 11 works. Negative 11 plus 11 is 0. And that's how it works. And no matter how long these expressions get, it boils down to that. Same thing over here, right? Either x minus 3 equals 0 or 2x plus 11 equals 0, because one of these has to equal 0. And so x equals 3 or x equals negative 11 over 2. The same 11 halves from the other ones. Okay? And that's kind of how it works. So we have one more here. Let me move this up. So in this case, we have three separate factors. We have an x plus 3, and a 3x minus 4. Well, this property applies to more than two things at the same time. If the product of three things equals 0, well, one of them's got to be equal to 0. So we would say x equals 0 or x plus 3 equals 0 or 3x minus 4 equals 0. So now the first one's kind of done for us, right? X equals 0, done. This one, as you could guess, should be negative 3. What about this one? Well, hard to see, right? But again, you may have to solve for x here. Add 4 to both sides. And then divide by 3. And you're going to get, so here 3x equals 4. Divide by 3, and I get x equals 4 over 3. This equation has three solutions: 0, negative 3, and 4/3. All three of those would be points on the x-axis. So the zero product property is a straightforward way to say, one of these factors has to equal 0. So no matter how weird the factors look, we can always solve to find those values. Okay, so let's look at a projectile problem. From lesson 2, we did a little bit of work in projectiles flying through the air. So here are two functions. We have one that is negative 5t squared plus 27t plus 18. And then the other one here is negative 5t minus 3 and t minus 6. These two functions are the same function. But one is in standard form and one is in factored form. So my first question is going to be, which is easier to figure out when the height is 0? So what does it mean for a projectile for the height to be 0? Well, the height is 0 when it's sitting on the ground, right? Ground is 0 meters off the ground. So height of 0 equals ground. So that's one thing to kind of think about. Basically, I'm asking here, when is this object hitting the ground? And we will interpret that as the height being 0. So if I plug in, so if the height of the object is 0, right? Say up here in these equations, these were zeros. Which equation is going to be easier to work with? The t squared and the t are going to be hard to kind of separate from one another. But this, remember, one of these factors has got to be equal to 0, right? So it's got to be that one. So use factored form. And we can do this without graphing, right? So at what time the height of the object is 0? Okay. I believe it should say on 0 to there. It does. Okay. So let's look at this function. So negative 5t minus 3 equals 0, or t minus 6 equals 0. So remember, t stands for time in these equations. So if I were to do this out, well, here's the easy one. Add 6 to both sides. T equals 6 seconds. But what about this one? If I add 3 to both sides, I get negative 5t equals 3, and then I divide by negative 5, and I get t equals negative 3/5 seconds. At what time does the height of the object become 0? Well, I got two answers, but now wait a second. This one is negative. So, negative time, is that really even really allowed? That's like traveling backwards in time. We can't do that. So, negative 3/5 is not valid. You can't have negative time. So, t equals 6 seconds. This object lands on the ground after 6 seconds because only that one answer happened to work. This is going to be common with projectile problems. You often get one answer that's positive and one answer that's negative. You get like a small negative answer and then one answer that's further out positive. And that's going to be the correct one because time has to go forward. All right. Hope you're with me so far. So, here's the official definition. The zero product property states that if the product of two numbers is 0, then at least one of the numbers must be 0. In other words, if a times b equals 0, then a equals 0 or b equals 0. That's the property that we did on the first few slides, just written out a little bit more algebraically. Just keep in mind, this only works for 0. There are no other numbers, not even 1, that this works for. So this product only works with 0. Only use if equals 0. If you have the product of equaling any other number, even 1 or 2 or 10 or anything, then this property cannot be used. There'll be infinite amounts of answers. Okay. So here's a few questions that kind of think about um, as we study this. So one, why is the factored form more helpful for finding the time when the object has a height of 0 meters? Well, if you think about this, so let's look at another sample equation that we have here. So if we have, say, like, um, t minus 3 times 2t plus 5 equals 0, something like that. Why is this better than the alternative? The easiest way to explain this is because you have the t is split to two factors and two easier equations plus it also gives you that, because now we know the zero product property, the factored form is always a product of two factors. So factored form is always of the form a times b equals 0. It's always a product of factors. What if we tried to solve the equation in standard form, right? So let's take one of the equations that we had before, and it doesn't really matter, so I'll just pick one even if it's not quite the right numbers. It was like negative 5t squared plus 27t plus 18 equals 0. It's an equation like that, right? Well, you might try solving it, right? And a lot of people will try solving this. So if you maybe subtract 18 from both sides, you get negative 5t squared plus 27t equals negative 18. The problem here that we get to is A, the equation no longer equals 0, and B, how do you split apart the t and the t squared? Dividing by t isn't going to help here simply because this 18 doesn't have a t on it. So we cannot divide, we cannot split or divide t easily here. There are methods for pulling this off and solving it from here, but they're quite complex. And that's something we're going to take a look at later, because there are some equations that cannot be written in factor form. But if we do have factor form, we should use it. The only thing you can do here, the problem is 5 and 27 also don't share any factors. So I can't really divide anything to simplify this. That's one of the problems we have with this. Okay, how does the zero product property help us to find solutions? So basically, we know knowing an expression has a product equaling 0. Means one piece equals 0. So it allows us to split this into two separate equations. And so it allows us to say x minus 3 equals 0 or x plus 4 equals 0. So basically, it's allowing us to split products into two separate equations only under the condition that it equals 0. Remember, 0 and no other number. Got that? Okay. All right. So here's an example of that. why are the solutions x minus 3 and x plus 4, like, why is this not 3 and negative 4? Well, you could say that, several reasons. One, doesn't equal 0, right? So it doesn't equal 0. Or, try plugging it in. If you tried plugging 3 in for x, you'd get 0. Negative 4, you'd get 0, not 8. But what if even you did this? What if you did, say you did x minus 3 equals 8, or x plus 4 equals 8? That's a common thing to try, saying like, oh, well, if the product equals 8, right? But think about this. This could be true, but only if this is 8 and this factor is 1, because 8 times 1 would be 8. But do these have to be 8 and 1? Well, not really. And besides, try solving it. Add 3 to both sides, and you get x equals 11, right? Now, what happens if you take 11 and plug it back into this equation? I would get 11 minus 3 is 8, and then I would get 11 plus 4, which is 15, and 8 times 15 is, well, not 8. It's 120, as a matter of fact. So, nope, not going to work here. All right, so right away, that's why this doesn't work out. So, anyway, let's not do that. And I'll just go ahead and erase this because that is bad. Bad, bad, bad. Don't do that. Okay. So another thing that's good to note here is that there are infinite pairs that multiply to 8. And actually, there's infinite pairs that multiply to any number except for 0. So 0 is the only one that has a limitation. But everything else, like 8, 7, even 1, like those numbers can freely change. Okay, the expression x squared plus x minus 12 is equivalent to x minus 3 times x plus 4. Can we apply the zero product property to solve this? Well, sure. If you can take this equation and convert it to that. And you might remember that process from Algebra 1. That's called factoring. So what we do is we can factor x squared plus x minus 12 to get x minus 3 times x plus 4. So we can do that math, right? And if we do, then we can set this equal to 0, and then we can say x equals 3 and x equals negative 4. So yes, we can, but with a step to write it in factored form first. Can we solve this equation by performing the same operation to both sides of the equation? You know what? I'm just going to say no. I'm not even going to try it because we know right away from our work before that that's just not going to work. The problem here is that splitting the x squared and the x just isn't going to yield anything that we like. You could try adding 12 to both sides, but then the equation no longer equals 0. So the whole point here is that instead, we're going to factor the equation like we did here. Okay. And that's really it for Lesson 3. Lesson 4 is pretty much the same thing. So I'm just actually going to go straight into this one here. And so that we can keep it on the same video, because the skill is actually really, really um, much the same. But there are some equations that we can also solve in a little bit of a different way, using much the same method. So the zero product property will come back again, but we're also going to take a look at a few other ways to determine solutions to quadratic equations. So now that we've done some work with the zero product property, our job now is to convert this to graphs, equations, and ultimately to our favorite term, x-intercepts. Okay, so there's a few things that we're going to look at here. One, explaining why dividing by a variable is not a good strategy. So I did say previously that, you could try dividing by x, try dividing by t, and it wasn't going to be very good, like this equation here. What would happen if I tried dividing by x? Well, I could divide that by x. I could divide that by x, but 12 I can't divide by x. So it's not a good strategy. Plus, there's a few other reasons too. So another thing that we're going to look at is that some quadratic equations actually don't have a solution. And we can also, from a graph, determine how many solutions that a quadratic can have. So you'll notice that some equations that we dealt with a few minutes ago had one answer, some had two answers, some even had three answers. Some equations have no answers. So we're going to look at a few of those. Okay, let's go on. All right, so here's a few equations here. Let's determine which ones are true or false. All right, number one, 3 is the only solution to x squared minus 9 equals 0. Okay, now is 3 a solution? Sure, 3 squared is 9, and 9 minus 9 is 0. So 3 does work. Can you think of any other numbers that you can square and subtract 9 and get 0? Well, let's see. 3 works. How about negative 3? Well, negative 3 squared is positive 9. So negative 3 also works. And so this one here is false. Okay, how about this equation? A solution to x squared plus 25 is negative 5. Okay, well, let's try it out. Negative 5 squared plus 25. Well, negative 5 times negative 5 is positive 25 plus 25, 50. So this one, also false. Okay. X times x minus 7 equals 0 has two solutions, right? So remember that we get x equals 0 or x minus 7 equals 0, zero product property. And therefore we get x equals 7. This one is true. Last one. 5 and negative 7 are the solutions to x minus 5, x plus 7 equals 12. Oh, is this the zero product property? Is this 12 product property? There is no 12 product property. This one's false. And you can prove it just by plugging one of them in, right? So if you plug in 5 in for x, remember that you'd be plugging 5 into both equations, right? The 5 goes in for both of them, and you get 0 times 12, which is, well, not 12. It's 0. So, not good. Same thing is going to happen if you did the negative 7. If you plug negative 7 in for both of them, you would get negative 12 times 0, which is also 0. So, nope. False, false, true, false. Okay. So here we have a person who solves three equations by graphing them. Okay. So graphing equations, well, we could pull up Desmos in a bit, but let's see what we can do without the graph first. Here we have x minus 5 times x minus 3 equals 0, but then the same one but equaling negative 1, and then also negative 4. Okay, so to solve the first equation, he graphs y equals x minus 5 times x minus 3 and looks for the x-intercepts of the graph. Oops. Does that work? Yeah, actually it does work. But do you know why? So the reason why that works is because solutions are x-intercepts, right? And another way for x-intercepts is an x-intercept is defined is where the function y equals 0. And we know that because it's sitting, x-intercepts sit on the x-axis, right? And so any point along this axis is going to be like 1 comma 0 or 3 comma 0 or negative 4 comma 0. Points like that. So in this particular case here, because we're setting y equal to 0, that's exactly what happened here. We have y, and it's been replaced with a 0. So, or in this case, he took the 0 and replaced it with a y and drew the graph. So that's really what he's looking for here, is this is synonymous with x-intercept. So what are the solutions? You could probably tell without graphing it at this point, it's x equals 5 or x equals 3, because those are the numbers here that make those factors equal to 0. Okay, to solve the second equation, now here's something interesting. Instead of graphing the equation exactly as it is, right? One of the problems that happens is here is that we have a number on both sides. So what Han does is he rewrites the equation by adding the 1 to both sides. And what that does is it puts the 0 on the right side of the equation. So that's an interesting one. So let's see if I could go ahead and do that here. I don't have Desmos up, but I can certainly pull that up here. Just give me a second, and here we go. And here's Desmos. And all right, perfect. You can see it right here with us. So what is the equation? Again, it is y equals, so let's type it in, y equals x minus 5, x minus 3, plus 1. Let me make sure that that equation matches what I have here. X minus 3, x minus 5, plus 1. Perfect. Okay. All right. So, whoopsie, and where's my Desmos? There's Desmos. Okay. What solutions do I have here? It looks like I have 4. So remember, we're looking for the x-intercepts. And in this particular case, we only have a single x-intercept, and that's at 4. So while I'm at it, let's go back to the other one. You can see on the original one how we have 3 and 5 both worked, right? 5 was an intercept, 3 was an intercept. But when I add the 1, now I have a single point of 4. The parabola only touches the x-axis once, and so it's only going to produce a single answer of 4. Okay. So in this case here, um, we graphed and we said that x equals 4. Since only 4 touches, actually no, it's not that the 4 touches the axis, so the graph so only once does parabola touch axis. Yeah, and so certainly if you did that, if you plugged 4 in for both x's, you would actually find that that does solve the equation because you get 4 minus 5 is negative 1. 4 minus 3 is positive 1, right? Negative 1 times 1 is negative 1 plus 1 equals 0, and it does check out. Now let's do the third equation. So I'm going to change this. So once again, we're going to take that equation, and we don't want the negative 4 on the right side, right? So I'm going to add 4 to both sides, and I'm going to have x minus 5, x minus 3 plus 4 equals 0, right? But that 0 I can think of as y on the graph, and so I will do that. So let's go to Desmos. 4. Oh, well, that's interesting. What are the x-intercepts? Okay, no x-intercepts. So what are the solutions? There are none. Ooh, the plot thickens. Okay. So if we come down here, sure enough, no x-intercepts. Therefore, no. So real solutions. The word real here, okay? More on that will come later on because it turns out, we can construct ways to identify solutions to this set, but in terms of an actual number line, there are no solutions to this. There's no number that we could physically plug in for x that would make this equation equal to 0. Try. You won't find one. And the reason is because the graph never crosses the x-axis. Okay. So why did we put the 0 on one side and then graph the expression on the non-zero side? Why did we do this? We did this so that this locates the solutions on x-axis. That's really why we do this, okay? Now, how many solutions did the graphs have? This one had 2 solutions, this one had 1 solution, and that one had none. And the first equation kind of did this. Swooped down through the axis, back up again. The second equation touched the graph just once. And then the third one didn't even bother touching the axis. It swooped down and back up, but only on one side of the axis. So it's important to see the difference between those two because that's the biggest way to tell whether there's two, one, or no solutions. Okay. Next question here. Let's look at finding all the solutions that we have to these equations. So we have x squared equals 121 and a whole bunch of other equations. So let's see what we can do in terms of finding solutions here. Now, we can do this through graphing, if you'd like, or we could do this through solving. Okay, let's just do this kind of with solving here first. X squared equals 121. So if we were to say, well, what value of x squared gives us 121? So x equals 11 is one of them, right? 11 times 11 is 121. But is that the only answer? Well, negative times negative is positive, right? Negative 11. So here, to show that, you can prove this. And you prove this by drawing the graph. So once again, what I would do is I would move the 121 over to the other side, and so I get x squared minus 121 equals 0. Let's draw that graph. Okay, let's go to Desmos, and let's do y equals x squared minus 121. And sure enough, you're going to see, here's the parabola, very skinny in this one, and it's got two solutions. One at 11, and the other one at negative 11. So there's your proof right there. Negative 11, positive 11. And we could do that as many times as we'd like. So let's look at a few others, shall we? How about this one? X squared minus 31 equals 5. Ew, 5, 31, ew, yucky numbers, right? But remember, having a 0 helps. So let's subtract 5 from both sides. And what's negative 31 minus 5? Well, x squared minus 36 equals 0. You could draw the graph of that, or, if you added the 31 instead, you could have x squared equals 36. So what numbers could I plug in for x here? Well, 6 times 6 is 36, right? So we know that x equals 6. And as you kind of guess from now, negative 6 will also work for this one, right? Because negative times negative is positive. What about this one? X minus 4 times x minus 4 equals 0. Well, let's see. Zero product property, right? Either x minus 4 equals 0 or x minus 4 equals 0. Hey, don't those give the same answer? If you get two of the same answer, you only have to write it once because the or is kind of moot there. X is both 4s, and so x is 4. So what about this one? X plus 3 times x minus 1 equals 5. Okay, so there's a few ways that we could do this one. Now, we could do some tricky algebra here. To do this algebraically, you'd actually have to multiply this out, subtract the 5 to get the 0, and then refactor it. That's kind of yucky. So when you have a situation like this, let's just draw the graph. We'll do x plus 3 times x minus 1 minus 5 equals 0. We're going to subtract the 5 from both sides. I'm just going to put that on the graph. X minus 3. Oops. Get rid of some stuff there. X plus 1 minus 5. That is correct, right? X plus 3, x minus 1 minus 5. Oh, plus 3 minus Okay, let's see the answers here. Looks like it crosses at -4 and 2. And it looks like those are going to be the answers for this. Yep, and they work. I am pleased to report that both of them will in fact work here. So -4 and 2. So here's a case where we kind of had to draw the graph for this one. So x equals -4 or x equals 2. So like I said, you can do that one algebraically, but that one will take a lot of work to do algebraically. We'll tackle that later. Okay, let's keep going. What about this one? X plus 1 squared equals -4. So once again, because it doesn't equal 0, let's make it equal 0. X plus 1 squared plus 4 equals 0. Hey, that looks like vertex form. Well, might as well do it. So x plus 1 squared plus 4. Okay, so, okay, we're looking for solutions along the x-axis. Nope. I'm seeing that's a big no here. So it turns out for this one, no solutions. And for this one, here's also a little bit of a trick that you can think about with this one. Notice that when you square something, this equation is saying that when you square it, you get a -4. Well, is there any number that you could multiply by itself to get a -4? Not really. So, no solutions here. This one is definitely won't have solutions. Okay, same thing with this one, right? 990 doesn't matter. No, let's just decimal set, right? So x minus 4, x minus 1 minus 990 equals 0. Let's see what happens. 4 minus 1 minus 990. So x minus 4, x minus 1 minus 990. Okay, we're going to have to zoom way out on this one. -34 is one of them. Oh, and -29 is the other. Would we really have gotten that? I mean, I'd fancy myself pretty good at math, but even I would have had trouble with that. So -29 and 34. So x equals -29 or x equals 34. Yikes. And sure enough, if I do in both cases, I end up with something like 33 times 30 in both cases, which is how that works. Just so that you knew. But yeah, that's how you solve using a graph. Okay. So, here's another kind of question that we can answer from this. Say that you have this equation x minus 5 times x plus 1 equals 7. Well, Priya reasons that if this is true, either x minus 5 equals 7 or x plus 1 equals 7. So the solutions are 12 and 6. Do we agree with that after all this lesson? No. Remember, this doesn't work. There is no 7 product property. that thinking does not work. In this case, must equal 0. So in this particular case, we have to graph. So the only way we have to do is you have to do x minus 5, x plus 1 minus 7 equals 0, then graph. That's really the only way you're going to handle that right now. Okay. Now here's an interesting question. X squared minus 10x equals 0. Diego says that to solve, we can divide both sides by x to get x minus 10 equals 0. So the solution is 10. Okay, fair enough, right? Because 10 minus 10 is 0. Maya says, I wrote the expression in factored form, which gives x times x minus 10 equals 0. Okay. So if you had a hard time trying to reading that, here's kind of visually what's happening. So Diego does this. He takes the equation x squared minus, clear that out. So he takes this equation and he divides everything by x, like this. Now x squared divided by x is just x. 10x divided by x is just 10, and 0 divided by x is just 0. He gets this equation, and he realizes that, well, there's only one answer. X equals 10. Okay, now Mai takes the same equation, x squared minus 10x equals 0, and writes the left side in factored form by factoring out an x to get x times x minus 10 equals 0. Then applies the zero product property and gets x equals 0 or x equals 10. So, one answer, two answers. Who's right? Well, if you compare the results here, 10 certainly does work, right? You get 100 minus 10 times 10. Yep, that works. But here, 0 also works, doesn't it? Because 0 minus 0 is 0. So, because we know 10 works, and 0 also does work in this equation, mine must be correct in this case. Well, it was more correct. Because it looks like we have two valid solutions instead of just one. So one of these equations went missing with Diego. Do you know why? So when you divide by x, this is a problem that happens when you're dividing by x. If x is potentially 0, in this case it is, well, what happens if x is 0? Well, now you're dividing by 0. And do we like dividing by 0? No, that's not a valid math operation. So it turns out you're hiding the fact by doing this. You're taking away the possibility of x being 0 because we're never allowed to divide by 0. And so it's like it's hiding. But if we factor instead of divide, that 0 never disappears. So in this case, we have a moral of the story. Don't divide by a variable if it may equal 0. Now, did we know that right away over here? No, we didn't. And sometimes We don't know that. The equation could be written in a way that we don't know that. And we divide by a variable, and we come to find out that, oops, 0 is possible. So we have to be careful. And it's a general rule of thumb to try not dividing by a variable if you can help it, unless you are absolutely certain that that variable can never be 0. So more on that later, but essentially right now, factor, don't divide. Okay, so real quick before we go here, um, quadratic equations can only have 0, 1, or 2 solutions, and that depends on where the graph is on the axis. So where it crosses x-axis. Oops. Um, so we can find out how many solutions a quadratic equation has by rearranging it so one side's equal to 0, okay? And then graphing the function, okay? And that's what we did in this unit. All right. And with that in mind, that's about it for here. So yeah, right around an hour, just the same as the last video. But this one's split into a couple parts. Okay, folks. So I'll put a chapter mark in for lesson 4 so that you can see it. And I hope you guys have a lovely night and use this video well. Take care.